In this lecture, we're going to do an example of a dynamic spring, or a spring that has a fatigue load on it. So let's begin with a description of the problem. We have a helical compression spring, and the spring is going to be preloaded with 60 pounds, and then it has a maximum load, or a working load, of 150 pounds over a dynamic deflection of 1 inch. So our working displacement will be 1 inch. The forcing frequency is 1,000 RPM, so it's running at 1,000 times per minute, and we're expecting it to last for 5 years of a single shift of operation. We're going to use music wire, since the loads are dynamic. We're going to use peening, which we discussed in the previous lecture, and we're going to recognize that this spring has not been set. So let's turn that into given values. Our minimum force is 60 pounds, maximum force is 150 pounds, our dynamic deflection, or Y work, is 1 inch. We have a forcing frequency of 1,000 RPM, and the life is 5 years at 1 shift. And then finally with steel, we have a modulus of rigidity of 11.5 MPSI. So let's start with some things that will be constant across the problem. The first one is the alternating force. Like we've done in most of our fatigue problems, we have a maximum minus a minimum over 2, and so 150 minus 60 divided by 2 is 45 pounds. We also have a mean force, which is 105 pounds. Cycles per year, just walk through this. What we mean by 1 shift is how long something is working for a typical work year. So that is 40 hours a week and 50 weeks a year. So that gives us 2,000 hours per year. And revolutions per minute, it's 1,000. And there's, of course, 60 minutes in an hour. So we have 1.2 times 10 to the 8th cycles per year. And we're going to do this for 5 years. So our final answer is 6 times 10 to the 8th cycles. All right, we're going to go ahead and pick a wire at this point. So the wire we're going to choose is 0.207. If you remember from last lecture, there's a reason we're choosing this diameter, or maybe a better way of saying it is the reason we chose to find SN curves for the 0.207 is so that it would be ready for this example. So if you're not familiar with the SN diagram generation, it would be good to go back and look at that video. But we're going to go ahead and assume a diameter of 0.07, and we'll also assume a spring index of 9. So that means that the coil diameter is 1.863. The next step is to calculate the stresses. And so we're going to do two different equations for stresses. We've seen both of them already. For the minimum and the mean stresses, since those are constant numbers, we're going to use that the shear stress is equal to Ks times 8FD over pi d cubed. We can calculate Ks. So applying this equation, first for the minimum stress, we'll apply the minimum shear stress is equal to that equation with F minimum applied, and that gives us about 34 KSI. And then for the mean stress, we'll do the same equation, but now applying F mean instead of F minimum, and that gives us about 59 KSI. For the alternating stress, we will need to use the wall constant instead of Ks, and so that constant's a little bit more. It's going to be 1.16, and so our alternating stress is again applying F alternating, and so that gives us 27, about 28 KSI. Just as a reminder, the reason we're using K, the wall constant as opposed to Ks, is because the set was not removed. If the set had been removed, even though this is a dynamic problem and even though we are looking at the alternating stress, we still would have been able to use Ks. All right, so from the last lecture, we calculated how to find all of the different values of strength of the wire at different numbers of cycles. So we looked at 1,000, we looked at 10,000, at 1,000,000, and then finally we found that the endurance strength occurs at 1 times 10 to the 10th cycles. And so we have a static strength of 0.6 of the ultimate strength, which is 143 KSI. That's the yield strength. And our ultimate shear strength is about 160 KSI. And if you recall from the last lecture, we were able to create a diagram that has there were different A and B values for each of these different ranges so that we could plot our SN diagram for the spring wire. Notice all of these strengths are talking about the strength of the wire and not the strength of the spring overall. So the next thing we need to do is we need to look at our modified Goodman equation. The SN values that we've always done in the past we're finding a strength up here on the top. So our SE or SN diagram, and when we looked at the modified Goodman diagram where we're comparing mean stress with alternating stress, we always did our experiments with all alternating and no mean stress. That's different now. Because the springs were loaded with repeated loadings as opposed to fully alternating loads, the value that we've been calculating has been where the mean and alternating are equal. In other words, we've been calculating this line. So our wire strength is actually this point B labeled here on the chart, not what we typically have done in the past has been point C. So we're not looking at the fully reversed case, we're looking at the case where the mean and alternating stress are equal to each other. So what we need to do now is we need to figure out how to convert this wire strength to a fully alternating strength or a fully static strength. And just like before, once we do that, we'll then have 4 cases. So going back to this modified Goodman line, the way we're going to find point C is simply by just using triangles and understanding that this is a 45 degrees. This is just basic geometry at this point. So I'll fast forward to the end and say that we can find the fatigue strength in shear, and it's going to be a function of the ultimate shear and this wire strength that we calculated from before. And there it is. There's our final answer. So applying that, we'll have about 48.5 KSI. Just to be clear, what I've already done at this point, this SFW was calculated using the number of cycles for our case. In our case, it was 6 times 10 to the 8th number of cycles. Going back to this diagram, 10 to the 8th, 6 is somewhere around here. So this was the number that we were calculating. That's the number that went into here and again here. So what we get out of that is actually a number quite a bit less, 48.5 KSI. Now, before, the way we found a factor of safety was looking at this equation. And if you notice what we have here, we have a fatigue strength, we have ultimate tensile strength, we have alternating stress and mean stress. Those are the components of this function. We're not going to be able to use that function this time. Instead, we're going to use this factor of safety equation. Let's take a look at the differences. The major difference that's coming here is a recognition that the preload is helping us. Notice here's our mean stress minus our initial shear stress. This is the shear stress coming from the minimum that will be applied. So what we've done is we're changing how much of the stress that the spring is seeing is alternating and how much of it is mean. And by increasing the amount of stress that is there all the time, what we're doing is we're decreasing the total mean stress that the spring is going to see as it stays there over time. So that gives us a factor of safety of 1.4. This is really important to understand that preloading the spring actually reduces the mean stress and therefore can increase our factor of safety. So from here, what do we do next? Well, we're going to choose the number of active coils to satisfy the desired K, and now it turns exactly into the same problem that we had before when we were calculating a static spring problem. So we'll find the number of K, we'll find the actual K and make sure it's satisfactory, we'll find the total number of coils, the initial flexion, the clash distance. We'll make sure that we still have a factor of safety for shutting the spring. I will mention for fatigue problems, most likely the factor of safety for fatigue will be conservative compared to the factor of safety to shut the spring. In other words, it's easier to shut the spring than it is to make it fail with fatigue. So we'll calculate a factor of safety to shut the spring, and then we also could check for buckling, which we won't do this semester, but in real spring design that is often an important component. And then as the spring is oscillating, since it's oscillating at a high rate of speed, you also should check for the natural frequency within the spring to make sure that the forcing frequency that the spring is undergoing is much lower than the natural frequency of the spring itself. And then report your final design decisions, and that finishes the problem.